Let's get right into it. Number 7. Proton decay. Right now, sitting wherever you are, your body is slowly disappearing, not in any way you can feel, not in any way any instrument on Earth can currently detect. But according to some of the most well-supported theories in physics, every single proton in your body, in every rock, every ocean, every star, has an expiration date. For most of the 20th century, physicists assumed protons were immortal. They're one of the fundamental building blocks of matter, and nothing seemed capable of destroying them. Then, in the 1970s, the grand unified theories arrived, and with them came an uncomfortable prediction. Protons do decay. They just do it so slowly we've never caught one in the act. The estimated half-life of a proton is at least 10 to the power of 34 years. For reference, the entire age of the universe is only 13.8 billion years. Written out, that's roughly 10 to the power of 10. Proton decay timescales make the current age of the universe look like the blink of an eye before a performance that runs for eternity. Scientists built massive underground detectors, like the Super Kamiokande in Japan, a tank containing 50,000 tons of ultra-pure water, specifically to catch a proton dying. Thousands of tons of matter watched 24 hours a day for decades. The result? Silence. Not a single confirmed proton death ever recorded. But here's what that silence means for the universe's future. If protons do eventually decay, the consequences are total. Hydrogen atoms collapse, stars can no longer form, white dwarfs, neutron stars. Every remnant of stellar life begins to slowly dissolve. By 10 to the power of 40 years, virtually all matter in the universe has quietly ceased to exist. What remains is a cold, dark, expanding void. Photons and a handful of lightweight particles drifting through a cosmos incomprehensibly larger and emptier than the one we know. The universe doesn't end violently at this stage. It ends the way a candle melts, slowly, completely, and without anyone left to notice. Number 6. Heat death. In 1850, physicist Rudolf Clausius introduced a concept that physicists have quietly dreaded ever since. He called it entropy, the tendency of any closed system to move irreversibly from order toward disorder. Pour cream into coffee, and it spreads out. It never spontaneously pulls back together. Clausius understood that this wasn't just a kitchen observation. Applied to the entire universe, it was a death sentence. The heat death of the universe, also called the Big Freeze, is the end state that follows from this law with mathematical certainty, assuming the universe continues expanding as it currently is. No explosion, no collision, no dramatic finale. Just a universe that runs out of usable energy and grinds to a permanent, motionless halt. Here's how it happens. Stars burn by converting matter into energy. But stars don't last forever. The most massive ones burn out in millions of years. Smaller stars, like red dwarfs, can last trillions, but even they eventually exhaust their fuel. As the last stars die and no new ones form, the universe enters what cosmologists call the degenerate era, a cosmos populated only by cold, stellar remnants, black dwarfs, neutron stars, and black holes. Then even those begin to go. Black holes, the most resilient structures in the universe, slowly evaporate over incomprehensible timescales through a process Stephen Hawking predicted in 1974. A black hole the mass of our sun would take 10 to the power of 67 years to evaporate completely. A supermassive black hole at a galactic center? 10 to the power of 100 years. When the last black hole evaporates, the universe contains nothing but a thin, cold haze of photons and particles separated by distances so vast that no interaction between them is ever possible again. Temperature approaches absolute zero. Every process that requires energy, every chemical reaction, every movement, every thought becomes impossible forever. The universe reaches thermodynamic equilibrium, maximum entropy, perfect, permanent stillness. Not death as we understand it, more like a universe that has simply forgotten how to do anything at all. Number 5. Big Rip. In 1998, two independent teams of astronomers made a discovery that rewritten cosmology overnight. They were measuring distant supernova, expecting to confirm that the universe's expansion was slowing down due to gravity. Instead, they found the opposite. The universe wasn't slowing, it was accelerating. Something was pushing space apart and getting stronger. They called it dark energy, and it makes up approximately 68% of everything in existence. Most models treat dark energy as a constant, a steady outward pressure that stretches the cosmos at a fixed rate. But some theoretical models propose something far more disturbing, that dark energy might be growing, getting stronger over time. And if it is, it leads directly to a scenario called the Big Rip. The timeline goes like this. First, dark energy overcomes gravity and tears apart galaxy clusters, scattering them across an ever-widening void. Then, individual galaxies are shredded, stars flung away from each other into permanent isolation. Then, solar systems break apart, planets drift away from their suns into the freezing dark. As the expansion accelerates further, the force tearing space apart becomes so extreme that it overcomes the electromagnetic bonds holding molecules together. Everything, rocks, oceans, the cells in your body, disintegrates into its constituent atoms. But the tearing doesn't stop. It accelerates. In the final fractions of a second before the Big Rip, the expansion overcomes the strong nuclear force itself. Atomic nuclei split apart. Protons and neutrons separate. Quarks, the most fundamental components of matter, are pulled away from each other into an expanding cloud of isolated particles scattered across a space growing faster than light can cross it. Some models predict the Big Rip could occur in as little as 22 billion years. The universe is currently 13.8 billion years old. We might be living in the first half of existence, in a cosmos already dominated by the force that will eventually reduce everything to nothing. And the worst part? We'd never see it coming. The acceleration would be invisible until the very end, and then it would be everywhere at once. Number 4. Big Crunch. For most of human history, people assumed the universe was static, eternal, unchanging, infinite. Then, in 1929, Edwin Hubble observed that every galaxy in the sky was moving away from us, and that the farther away it was, the faster it receded. The universe was expanding. It had a beginning. And some cosmologists began asking, does it also have an end? Not in slow dissolution, but in violent reversal? The Big Crunch scenario begins with a premise. What if gravity wins? What if the expansion of the universe eventually slows, halts, and reverses? What if everything that has ever flown apart begins, across billions of years, to fall back together? The reversal would be imperceptible at first. Distant galaxies would slow their retreat and stop, like a stone thrown upward reaching its peak. Then they'd begin to fall back inward, slowly at first, then faster. The cosmic microwave background radiation, the faint afterglow of the Big Bang, currently chilled to just 2.7 degrees above absolute zero, would begin to warm as the universe contracted. Galaxies would begin merging into each other. The night sky would grow brighter as stars crowded closer together. As the collapse accelerated, individual galaxies would be compressed into a single fireball of matter and energy. Stars, planets, everything would be crushed and fused into a superheated plasma. Space itself would collapse. In the final moments, conditions would mirror those at the very beginning. A universe compressed to an unimaginably hot, dense singularity where the laws of physics as we understand them completely break down. Here's the part that keeps cosmologists up at night. If the Big Crunch occurs, if everything collapses back into a singularity, we have no theory that can tell us what happens next. Physics simply ends. The equations break. What becomes of time, of space, of the information that described 100 billion galaxies? Nobody knows. There is no after. There may not even be a concept of after left to have. Number 3. Big Bounce. The Big Bounce takes the most disturbing part of the Big Crunch and makes it worse, because it proposes that a collapsing universe doesn't simply end at the singularity. It bounces, it rebounds, it explodes outward again in a new Big Bang, and it has done this before, possibly an infinite number of times. The idea has ancient roots. Cyclic cosmology appears in Hindu philosophy, in Stoic thought, but its modern scientific version was developed in the early 2000s by cosmologists Paul Steinhardt and Neil Turok. Their cyclic model proposes that the universe has no true beginning and no true end. Instead, it passes endlessly through periods of expansion, contraction, singularity, and rebirth. At first glance, this sounds almost comforting. The universe gets a reset button. But look closer. If the Big Bounce is real, our universe, every star, every galaxy, every human civilization that has ever or will ever exist, is just one chapter in a story with no beginning and no end. Not special, not unique, not the first, and not the last. Every configuration of matter that can exist has already existed. Somewhere in the infinite history of bouncing universes, a version of you has lived this exact moment before, multiple times, across cycles of time so vast, they make our current universe look like a single page in a library without walls. Worse still, each bounce erases everything that came before it. The laws of physics may be reset with each cycle. Any structure, any information, any civilization sophisticated enough to survive the crunch, all of it annihilated in the singularity, replaced by something new. The universe has no memory. It is a story told by a narrator who forgets everything at the end of every chapter and begins again, with no knowledge that there was ever a chapter before. How many times has it bounced? There's no way to know. And there's no version of you that survives to find out. Number 2. Brane Collision. To understand this one, you need to accept something that sounds like science fiction, but is treated seriously by theoretical physicists working at the cutting edge of cosmology. Our universe may be a membrane, not a metaphor, a literal, physical, higher-dimensional membrane, called a brane, floating in a vast extra-dimensional space that physicists call the bulk. This idea comes from string theory and M theory, frameworks developed to reconcile quantum mechanics with general relativity. In these models, the three dimensions of space we experience are a surface, a brane, embedded in a higher dimensional reality we can never directly observe, and we are not alone in the bulk. Other branes exist. Parallel membranes, potentially containing parallel universes with their own physics, their own matter, their own histories. Here's where it becomes terrifying. These branes are not stationary. They drift through the bulk. And if two branes collide, if our membrane intersects with another, the energy released in that collision would be unimaginably catastrophic. Some models propose that the Big Bang itself was exactly this. A collision between our brane and another, releasing the enormous energy that created everything we know. If that's true, it means our universe was born from a catastrophe, and it means another catastrophe could happen again. Another brane could be drifting toward ours right now through dimensions we cannot perceive, at a velocity we cannot measure. The collision would propagate at the speed of light. There would be no warning, no precursor, no signal we could detect in advance. One moment, the universe exists. The next moment, a wall of energy traveling at light speed has obliterated every galaxy, every star, every atom in its path, replacing them with the conditions of a new Big Bang, seeding a new universe from the ashes of ours. We wouldn't see it coming. We couldn't. And from our perspective, it wouldn't even take a moment. It would simply be the last thing that ever happened. Number 1. Vacuum decay. In 2012, scientists at CERN announced the discovery of the Higgs boson, the particle responsible for giving all other particles their mass. The physics community celebrated, but hidden in the measurements was a number that made cosmologists go very quiet. The mass of the Higgs boson came in at approximately 125 giga-electron-volts. That specific value, combined with the mass of the top quark, places our universe in what physicists call a metastable vacuum state. Not the lowest possible energy state, not the most stable configuration reality could take, just stable enough, for now. Think of it like this. The universe is a ball resting in a valley on a hillside. It's not rolling anywhere. It seems perfectly still, but just over a ridge you can't see from where you're standing, there's a much deeper valley. All it takes is enough energy to push the ball over the ridge, and it falls. And it never comes back. In our universe, that ridge is called the false vacuum. Our entire reality, every law of physics, every force, every particle, is maintained by the current energy state of space itself. But quantum mechanics allows for something called quantum tunneling, the possibility that a region of space could spontaneously transition to the true vacuum, the lower energy state, without any external trigger. No warning, no cause. It simply happens. The result is a bubble, called a vacuum decay bubble, expanding at the speed of light in all directions, converting everything it touches into a universe governed by completely different physical laws. Laws incompatible with matter as we know it. Laws incompatible with atoms, with chemistry, with life of any kind. Inside the bubble, reality as we understand it ceases to exist. Here is the part that separates vacuum decay from every other scenario on this list. There is no escape. There is no preparation. The bubble travels at light speed, meaning the first moment you could ever detect its existence is the same moment it reaches you. By the time any information about its approach could possibly reach us, it's already here. Not here the way a storm approaches from the horizon. Here the way a thought arrives, instantly and without predecessor. Physicist Sidney Coleman, who developed much of the theoretical framework for vacuum decay in 1980, showed that such a bubble, if formed, converts everything inside it into a state of lower energy. No explosion visible from outside, no debris. The region simply changes, becomes something other than what it was. The most unsettling thing about vacuum decay isn't the destruction, it's the silence. A bubble could be expanding across the Milky Way right now, erasing galaxies one by one, and we would have no idea. No telescope can outrun light, no signal can precede it. The universe could be ending, right now, in a direction we've never thought to look, and we'd only know in the instant we stop knowing anything at all. That's it for today. Subscribe for more.